Tonight, we're going to explore one of the most remarkable journeys in human history. Two spacecraft launched in 1977 designed for a 5-year mission to study Jupiter and Saturn. They're still operational nearly 50 years later, billions of miles beyond their original destination. And when they reached the edge of the solar system, they discovered something shocking. The boundary was 2.4 billion miles farther than every scientist predicted. The shape was completely wrong. The magnetic field behaved in ways no one expected, and the space beyond had properties that contradicted every model. 7 major discoveries that proved we didn't understand our own cosmic neighborhood. By the end of tonight, you're going to understand how 2 spacecraft built with 1970s technology rewrote our understanding of where the solar system ends and interstellar space begins. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The year is 1977. NASA launches 2 identical spacecraft on what everyone expects to be a 5-year mission. Voyager 2 lifts off on August 20th from Cape Canaveral. Voyager 1 follows on September 5th, taking a faster trajectory that will allow it to reach Jupiter and Saturn first. The names reflect their arrival order, not their launch sequence. Each spacecraft weighs 1,820 pounds. They stand 12 feet tall, and they carry a suite of instruments designed to study Jupiter and Saturn, the 2 largest planets in our solar system. The mission is called the Grand Tour, taking advantage of a rare planetary alignment that occurs once every 176 years. This cosmic arrangement allows the spacecraft to use gravity assists, slingshotting from one planet to the next, visit all 4 outer giants, Jupiter, Saturn, Uranus, and Neptune in a single journey. Without this alignment, visiting all 4 planets would require separate missions and far more fuel than any rocket could carry. The planets have arranged themselves perfectly. NASA seizes the opportunity. The original plan is simple. 5 years study Jupiter and Saturn, then drift into the outer solar system as the power fades. Music and instruments go silent. No one expects these spacecraft to last beyond their warranty. No one predicts they will still be operational in 2026, nearly 50 years later. And absolutely no one anticipates that their greatest discoveries will come not from the planets, but from what lies beyond them, from a boundary that scientists thought they understood. But here's what scientists in 1977 believed about the edge of the solar system. They knew the sun constantly emits a stream of charged particles called the solar wind. This wind flows outward in all directions at speeds around 250 to 500 m/s. It's a plasma, a soup of protons and electrons so hot that atoms are ripped apart. The solar wind was discovered in the late 1950s and early 1960s. Eugene Parker, a physicist at the University of Chicago, predicted its existence based on theoretical calculations. He showed that the sun's corona, the outermost layer of the solar atmosphere, is so hot that it can't be gravitationally bound. The gas must flow outward continuously. Parker's prediction was controversial at first. Some scientists thought the solar wind must be transient, occurring only during solar storms. But spacecraft measurements in the early 1960s confirmed that the solar wind flows continuously, every day, every year, regardless of solar activity level. The sun is constantly losing mass through this wind. About 1 million tons per second. That sounds like a lot. but the Sun is so massive that it would take trillions of years to lose a significant fraction of its mass this way. Eventually, this solar wind has to hit something. It can't expand forever. The galaxy isn't empty. Between the stars, there's gas, extremely thin, but it's there. About 0.1 atoms per centimetre for comparison. Earth's atmosphere at sea level has about 10 to the 19th atoms per centimetre. So interstellar space is 10 to the 19th times less dense than air. It's a better vacuum than we can create in our best laboratories, but it's not nothing. Over cosmic distances, even this tenuous gas has mass, pressure, and momentum. The interstellar medium is also moving, not because it has its own bulk flow, but because the Sun is moving through it. Our entire solar system orbits the galactic centre about 137 mph. That's about 490,000 mph. From the Sun's reference frame, the interstellar medium is a headwind blowing past at that speed. Where the solar wind meets the interstellar medium, a boundary forms. Scientists call it the heliopause, the place where the Sun's influence ends and true interstellar space begins. The place where the outward pressure of the solar wind equals the inward pressure of the interstellar medium. Beyond the heliopause is space that's no longer dominated by the Sun, space where the galactic magnetic field dominates, where galactic cosmic rays flow freely, where the properties are determined by the galaxy rather than by our star. By the 1980s and 90s, scientists had built sophisticated computer models of this boundary. They ran three-dimensional magneto-hydrodynamic simulations. These simulations included magnetic fields, plasma dynamics, and the effects of the Sun's motion through the interstellar medium. They predicted the heliopause would be roughly spherical, maybe slightly elongated like a comet's tail, maybe somewhat elongated in the direction opposite the Sun's motion, forming a tail, but basically symmetric, a bubble surrounding the Sun at a fairly consistent distance in all directions. They calculated it should be at about 90 to 100 astronomical units from the Sun. 1 AU is the distance from Earth to the Sun, roughly 93 million miles. So 90 to 100 AU meant about 8.4 to 9.3 billion miles. This seemed reasonable based on the data available. Models assumed the interstellar medium was fairly uniform in density and pressure. They assumed the Sun wasn't moving too fast through it. They assumed the solar wind output was fairly constant. All reasonable assumptions based on limited data available in the 1980s and 90s. They knew the solar wind strength from measurements near Earth. They estimated the interstellar medium's pressure from astronomical observations. They ran the equations 90 to 100 AU. That's where Voyager should cross. Before reaching the heliopause, the solar wind would encounter a shock wave called the termination shock. This happens because the solar wind is supersonic. It's moving faster than the speed at which pressure waves can travel through the plasma. The speed of sound in a gas depends on temperature and composition. In the solar wind plasma, the sound speed is typically around 30 to 60 IGA per s. The solar wind is flowing at 250 to 500 mm per s. So, it's moving at 5 to 10 times the sound speed. It's supersonic, or more precisely supermagnetoic, because magnetic fields affect wave propagation in plasma. When supersonic flow encounters an obstacle, a shock wave forms ahead of the obstacle. This is true in air, which is why supersonic aircraft create sonic booms. It's also true in plasma. At the termination shock, the solar wind would suddenly slow down from supersonic to subsonic from about 250 to 500 per s, down to maybe 50 to 100 m per s. The plasma would heat up and compress. The density would increase by a factor of 3 or 4. The temperature would jump by an even larger factor. Energetic particles would be accelerated by the shock, boosted to high energies by the electromagnetic fields associated with the shock structure. Models predicted the termination shock would be somewhere around 75 to 90 AU, somewhat closer than the heliopause itself. The exact distance would depend on solar activity. During solar maximum, when the sun is producing more solar wind, the increased pressure would push the termination shock farther out. During solar minimum, less solar wind and the shock would move inward. Between the termination shock and the heliopause would be a region called the heliosheath, solar wind plasma that's been slowed and heated, flowing generally outward but also sideways, trying to move around the obstacle of the interstellar medium. The flow in the heliosheath wouldn't be smooth. It would be turbulent, filled with magnetic field irregularities and plasma instabilities, but it would still be dominated by solar material particles that originated from the sun. The heliosheath was expected to be perhaps 10 to 20 AU thick, a transition zone between the shocked, solar wind and true interstellar space. Beyond the heliopause, galactic cosmic rays would dominate. High-energy particles from supernova explosions and other violent events across the galaxy. These particles are mostly blocked from the inner solar system by the sun's magnetic field and the solar wind. They can penetrate into the heliosphere, but their intensity is reduced. The heliosphere acts as a shield, deflecting or slowing many cosmic rays before they reach the inner planets. But beyond the heliopause, their intensity would increase significantly. Models suggested cosmic ray intensity might double or triple compared to levels at Earth's orbit. The transition across the heliopause should be fairly sharp. Models suggested it might take a few weeks to a few months at most to cross from the heliosheath into interstellar space. The spacecraft should see solar wind plasma disappear suddenly, or at least drop to very low levels. Galactic cosmic rays should suddenly increase. The magnetic field direction should change as the spacecraft encountered the galactic magnetic field instead of the sun's field. The galactic magnetic field was expected to be oriented differently from the sun's field. The sun's field in the heliosphere runs generally radially outward from the sun. Though twisted and tangled by the sun's rotation, the galactic field should be oriented based on the large-scale structure of the Milky Way. Model suggested it should make a significant angle relative to the radial direction from the sun, so at the heliopause crossing instruments should detect all of these changes: plasma disappearing, cosmic rays increasing, magnetic field rotating to a new direction, all happening over a period of weeks to months. Scientists were confident in the basic picture. The equations of magnetohydrodynamics were well established. The physics of shocks and plasma dynamics had been studied for decades. The models had been refined and improved over years of work. They might be wrong about the exact distances, but the overall structure should match the models: termination shock around 75 to 90 AU, a heliosheath 10 to 20 AU thick, a heliopause around 90 to 100 AU, a clear, relatively sharp boundary separating solar and interstellar space. But they were wrong. Not slightly wrong, dramatically wrong. And that was just the first surprise. Understanding what makes these discoveries so remarkable requires understanding the technology that made them possible. Because what Voyager accomplished, it accomplished with equipment designed and built in the early 1970s. Before personal computers, before the internet, before cell phones, the computers aboard each Voyager are absurdly primitive by modern standards. Each spacecraft has 3 computer systems working together. The computer command system handles instructions from Earth. The flight data system processes science data. The attitude and articulation control system manages orientation and pointing. Together, these three systems have about 68 kilob of memory. Your smartphone has millions of times more memory than both Voyagers combined, yet engineers can still upload software patches to these machines. In 2002, NASA uploaded new code to Voyager 1 to work around a failing memory module. In 2013, they switched Voyager 2 to backup thrusters that hadn't been used in 37 years. The thrusters fired perfectly. Imagine debugging software written 50 years ago running on hardware you can't touch, where every command takes over 22 hours to reach its destination. Power comes from radioisotope thermoelectric generators, RTGs. 3 per spacecraft, they contain plutonium, 238, which decays naturally and produces heat. Thermocouples convert that heat into electricity at launch. Each spacecraft generated about 470 W, but plutonium decays over time. The power output drops steadily about 4 watts per year. By 2026, Voyager 1 has only about 249 watts remaining. This declining power is the ultimate constraint. Every instrument, every heater, every transmitter draws from this dwindling budget. As power drops, engineers must decide what to shut down. The cameras went dark in 1990. Various instruments have been turned off over the years. By the late 2020s, there won't be enough power to run anything. The spacecraft will fall silent. Communication happens through the Deep Space Network. 3 massive radio antenna complexes in California, Spain, and Australia spaced around Earth, so at least one always has a view of the spacecraft. Each antenna is 230 feet in diameter. The signal from Voyager 1 takes over 22 hours to reach Earth. The signal from Voyager 2 takes about 18 hours. When engineers send a command, they wait those hours for it to arrive, then wait again for confirmation. A simple exchange takes over 44 hours for Voyager 1. The transmitter power from each spacecraft is about 23 watts, less than a typical LED light bulb. By the time that signal reaches Earth across billions of miles, it's incredibly faint. 1/quintillionth of a watt, the faintest signal humans routinely detect and decode. This is the technology that discovered what lies at the edge of the solar system: computers. With less memory than a microwave oven, transmitters weaker than a refrigerator light bulb, instruments designed with slide rules. Keep this in mind as we explore what they found, because what comes next shocked every scientist who studied the data. Voyager 1 reaches the termination shock on December 16, 2004. The spacecraft is at 94 AU from the Sun, 8.7 billion miles. Scientists had predicted the termination shock would be at 75 to 90 AU. Voyager is already beyond that range. The termination shock is where the solar wind suddenly slows from supersonic to subsonic speed. It's a real physical boundary where the plasma compresses and heats up. And Voyager just found it farther out than expected. But here's where it gets strange. The crossing isn't clean. Voyager detects the shock on August 1st, 2002 at 85 AU. Then the shock moves. Over the following months, the boundary shifts outward. Voyager finds itself back in supersonic solar wind. The signatures of the shock disappear. In 2003, Voyager detects it again. The shock washes over the spacecraft as it moves outward, then retreats. Finally, on December 16th, 2004, Voyager crosses and stays in the slower, denser plasma beyond. This breathing motion of the boundary is caused by solar activity. When the sun has strong outbursts, The increased solar wind pressure pushes the shock farther out. When activity drops, the shock moves inward. The boundary is dynamic, not static. Voyager 2 crosses the termination shock on August 30th, 2007 at 84 AU, 7.8 billion miles. Wait. Voyager 2 crossed closer to the Sun than Voyager 1 did, about 10 AU closer, 930 million miles closer. If the boundary is spherical, both spacecraft should cross at roughly the same distance. This is the first solid evidence that the shape is wrong. The heliosphere isn't a simple bubble. It's compressed in some directions, extended in others. Voyager 1 is heading toward the nose, the direction the Sun moves through the galaxy. Voyager 2 is heading more toward the side. The nose is compressed by the Sun's motion like a bow wave in front of a moving boat. The sides and tail are stretched out. The two Voyagers are sampling different parts of a complex asymmetric structure. Scientists had suspected this might be the case. Now they have proof. After crossing the termination shock, both Voyagers enter a region called the heliosheath. This is supposed to be straightforward. Slowed solar wind plasma flowing outward and sideways, turbulent but predictable. A transition zone between the shocked solar wind and interstellar space. Scientists expect Voyager to spend 5 to 10 years crossing this region before reaching the heliopause. The heliosheath should be 10 to 20 AU thick. Based on Voyager 1's position and speed, crossing should happen around 2015 at about 100 to 110 AU. But starting in 2010, something unexpected happens. Voyager 1 begins detecting increasing levels of galactic cosmic rays. These are high-energy particles from supernova explosions and other violent events across the galaxy. Their intensity should increase sharply at the heliopause in the middle of the heliosheath. At the same time, lower-energy particles from the Sun are decreasing. Solar particles should disappear at the heliopause, not gradually fade away beforehand. Voyager is still clearly in the heliosheath. Instruments still detect solar wind plasma. The magnetic field still has characteristics of the Sun's field. So what's happening? In June 2012, Voyager 1 detects something completely new. A region where the magnetic field lines align directly. Radially, pointing straight outward from the Sun, not tangled, not twisted, perfectly organized, and particles are flowing along these field lines in both directions. Solar particles flowing outward, galactic cosmic rays flowing inward. The field lines are acting like a highway connecting the heliosheath to interstellar space. Scientists call it the magnetic highway. No model predicted this. No one anticipated a structure like this could exist. The leading theory is that the Sun's magnetic field is connecting to the galactic magnetic field where field lines merge. Particles can flow freely both ways. It's like a bridge between two otherwise separate regions. Voyager 1 spends about 2 months in this magnetic highway. During this time, cosmic ray intensity is higher than anywhere else in the heliosheath. Solar particle intensity is lower. The spacecraft is sampling a region with direct access to interstellar space, even though it hasn't crossed the helop yet. Then on August 25th, 2012, everything changes. Solar wind particles essentially vanish. Cosmic rays jump to a high steady level. The change happens over a few days, but the magnetic field direction doesn't change. It keeps pointing the same way it was pointing throughout the heliosheath. This causes confusion. Some scientists argue Voyager has crossed the heliopause. The disappearance of solar particles and surge in cosmic rays suggests it has. Others argue the lack of magnetic field rotation means it hasn't. Maybe it's in some intermediate region. Maybe the helop has multiple layers. The debate continues for over a year. Finally, In September 2013, NASA officially announces Voyager 1 crossed the heliopause 2012. The spacecraft is at 121 AU, 11.22 billion miles from the Sun, far beyond where models predicted, not 90 to 100 AU, 121 AU, 20 to 30% farther than expected. 2.4 billion miles beyond the predicted boundary. This is shocking discovery number 1. The heliopause isn't where scientists thought it would be. And it's not just a small error, it's billions of miles off. This means either the solar wind is stronger than models assumed, or the interstellar medium is weaker than estimated, or both. Later analysis suggests the local interstellar medium is less dense than scientists thought, not dramatically less dense, but enough to shift the balance point outward by 20 to 30%. This matters because the heliosphere shields the inner solar system from galactic cosmic rays. A larger heliosphere means better shielding. It affects cosmic ray exposure on Earth over geological timescales which could influence climate, atmospheric chemistry, even mutation rates. But distance isn't the only surprise. Scientists expected the heliosphere to be roughly spherical, maybe elongated opposite the Sun's motion, forming a tail like a comet, but basically symmetric. The reality is very different. The heliosphere is shaped more like a bullet or teardrop. The front, where the Sun moves through the interstellar medium, is compressed into a blunt nose, the sides are flattened, the tail stretches out behind for potentially hundreds of AU. Voyager 1 crossed at 121 AU, heading roughly toward the nose. Voyager 2 crossed on November 5, 2018 at 119 AU. Voyager 2 is heading in a different direction, more toward the flank. Both crossed at roughly the same distance from the Sun. This tells us the heliosphere isn't dramatically elongated at the equator. The asymmetry is more subtle. The compression comes from the Sun's motion through the galaxy. The Sun moves at about 137 mph music relative to the local interstellar medium. That's about 490,000 MPa from the Sun's reference frame. The interstellar medium is a headwind hitting the heliosphere from the front. This compresses the nose. Outside the heliopause, there should be a bow shock in the interstellar medium, similar to a bow wave in front of the boat. Models predict this shock at around 140 to 230 AU. But given how wrong the models were about the heliopause, the bow shock could be anywhere. The Voyagers haven't reached it yet. The shape matters for cosmic ray access to the inner solar system. If the heliosphere was spherical, cosmic rays would have equal access from all directions. With a bullet shape, they can penetrate more easily from some directions than others. The tail might provide an easier path for cosmic rays to reach us from behind. The shape also affects how the solar system interacts with structures in the interstellar medium. Our Sun is moving through a region called the local interstellar cloud, a slightly denser patch of the interstellar medium a few light-years across. The boundaries of this cloud affect how the heliosphere is compressed in thousands of years. The Sun will move out of this cloud into a different region. The interstellar pressure will change. The heliosphere will change shape and size. The Voyagers are giving us a snapshot of the boundary as it exists now. Future spacecraft might measure a very different structure. This is shocking discovery. Number 2. The shape is wrong, asymmetric dynamic, influenced by the Sun's motion through the galaxy. Not the simple bubble scientists predicted. Scientists expected crossing from the heliosheath into interstellar space to be relatively clean, a boundary where over a few weeks or months solar plasma disappears, cosmic rays increase, and the magnetic field reorients, a clear transition instead. Voyager 1's approach to the helipore takes over 2 years. Starting in 2010, cosmic rays gradually increase, but the spacecraft is still detecting solar plasma. In 2012, it enters the magnetic highway, an unexpected structure where particles flow along field lines connecting the heliosheath to interstellar space. On August 25, 2012, solar particles vanish. Cosmic rays jump up, but the magnetic field doesn't rotate. This creates months of debate. Finally, scientists realize the galactic magnetic field happens to run roughly parallel to the Sun's field in this region. Pure coincidence. Crossing the boundary doesn't cause a dramatic field rotation because both sides point the same way. Voyager 2's crossing is different. It happens over about 1 day on November 5th, 2018, much faster than Voyager 1, and Voyager 2 detects a clear change in magnetic field direction. About 20 degrees rotation, not a dramatic flip, but measurable. Why the difference? The two spacecraft crossed in different locations. The boundary structure isn't uniform. At Voyager, one's location near the nose. The heliosphere is compressed. The boundary might be thicker or more structured. The magnetic highway phenomenon might be more common there. At Voyager 2's location toward the side, the boundary is sharper, the transition faster, the magnetic geometry different. Both spacecraft also detect oscillations after crossing. Voyager 1 briefly detects solar particles again in August 2013, nearly a year after crossing. Then they disappear again. The boundary washed over the spacecraft, then receded. These oscillations are caused by solar activity. Strong solar wind bursts travel outward through the heliosphere. When they hit the helipore, they temporarily push it outward. The boundary expands past a spacecraft, then contracts when the pulse dissipates. Voyager caught the helipore breathing, expanding and contracting in response to solar storms billions of miles away. The pressure wave from a storm in 2012 might not reach the boundary until 2014 or 15. This dynamic behavior wasn't predicted. Models treated the helipore as stable, moving slowly over years in response to the solar cycle, not oscillating rapidly over weeks or months, not moving enough for a stationary spacecraft to cross back and forth without actually moving. The boundary of the solar system isn't fixed. It's not a line you can draw and say, here it ends. The boundary moves sometimes by several AU over short timescales. If you're at 120 AU, are you in the solar system or interstellar space? The answer depends on when you ask right now. Maybe interstellar space. Next month, after a solar pulse arrives. Maybe back in the heliosheath a few months later. Interstellar space again. This is shocking discovery number 3. The transition is complex, prolonged, and dynamic. Multiple crossings, the magnetic highway, oscillations. Nothing like the clean boundary scientists predicted. Voyager 1 is the first spacecraft to directly sample the interstellar medium before Voyager. All knowledge of interstellar space came from remote observations, spectroscopy of distant stars, radio observations of hydrogen clouds, theoretical models. Voyager measures it directly, sticks instruments into it, and takes readings. The density is about 0.08 particles per cubic cm. The best vacuum chambers on Earth achieve densities around 1 million particles per cubic cm. Interstellar space is a better vacuum than we can create in our best laboratories, but it's not empty. 0.08 particles per centimeter means 80,000 particles per cubic meter. A cubic meter of air at sea level contains about 10 to the 25 particles. Interstellar space is about 10 trillion times less dense than air, but it's not nothing. The temperature is about 54,000 to 90,000 degree F. Sounds hot, but temperature measures average kinetic energy of particles, not heat content. With so few particles, even high temperature doesn't mean high heat. An astronaut in interstellar space would freeze, not burn, not enough particles to transfer heat. The pressure is about 0.000000003 pascals. Earth's atmospheric pressure at sea level is about 101,000 pascals. Interstellar pressure is roughly 110 trillionth of Earth's. But this pressure balances the solar wind at the heliopause. Even though it's extraordinarily tenuous, it's enough to stop the sun's outflow. Voyager detects plasma oscillations in the interstellar medium, waves of compression and rarefaction travelling through the plasma. In 2012 and 2013, Voyager 1 detects several bursts of oscillations. The frequency allows scientists to calculate electron density. Different measurements give slightly different values. The density isn't perfectly uniform. It varies by 10 to 20% over distances of a few AU. These variations affect how the heliopause is structured. Denser regions push harder on the heliosphere from that direction. Less dense regions allow it to expand farther. The interstellar medium is also magnetized. It contains a magnetic field part of the galaxy's overall structure. Voyager 2 measures the field strength at about 50 nanotesla. Earth's magnetic field at the surface is about 50,000 nanotesla. The interstellar field is about 1 millionth as strong as Earth's. But over vast distances, even this weak field has significant effects. It shapes plasma flow. It accelerates cosmic rays. It connects star systems across the galaxy into a web of field lines. None of these properties match predictions exactly. Models suggested similar values, but actual measurements consistently differ. Density a bit higher or lower than expected. Temperature slightly different. Magnetic field strength and orientation not quite what models predicted. Every measurement refines his understanding and forces scientists to update models. This is shocking discovery. Number 4. Interstellar space properties don't match the models. The first direct measurements reveal differences in density, temperature, pressure, and magnetic field. Small differences, but enough to music matter. One of Voyager, one's most surprising findings, is detecting what scientists call tsunami waves. Shock waves travelling through the interstellar medium caused by the Sun, when the Sun produces a powerful outburst, a coronal mass ejection or strong solar wind burst. That pulse travels outward through the heliosphere. When it reaches the heliopause, it hits like a hammer. The impact launches a shock wave into the interstellar medium. These waves travel at the sound speed in the interstellar plasma, about 60 m/s, much slower than the solar wind, but fast enough to cross several AU in a year. Voyager 1 detects the first tsunami in October and November 2012. The plasma wave instrument detects oscillations lasting several weeks. Specific frequency allows calculating electron density. A second tsunami arrives in April and May 2013, different frequency indicating density has changed slightly. A third in March 2014, a fourth in 2015. Each wave traces back to a solar event years earlier. The Sun has a major outburst. The pulse travels outward at supersonic speed through the heliosphere, hits the heliopause, launches a shock wave into interstellar space. Months or years later, Voyager detects the music wave passing over it. This reveals the Sun's influence extends far beyond the helop, not as solar wind plasma, which is confined to the heliosphere, but as pressure waves, shock waves that travel through the interstellar medium. These waves probably don't travel indefinitely. They gradually dissipate as energy spreads over larger area, but they can travel significant distances, possibly tens of AU beyond the heliopause. The detection also confirms Voyager crossed the heliopause. The waves come from the sun's direction. They travel through interstellar plasma. If Voyager was still in the helios sheath, it would detect solar wind pulses directly, not shock waves propagating through the interstellar medium. Tsunami waves were completely unexpected. No model predicted the sun's outbursts would be detectable by a spacecraft in interstellar space. Scientists knew shock waves existed in the interstellar medium from supernovas, but shock waves from the sun detectable billions of miles beyond the heliopause. This is shocking discovery number 5. Tsunami waves from solar storms propagate through interstellar space. The sun's influence reaches farther than anyone imagined. This is perhaps the most puzzling discovery. Magnetic field orientation in interstellar space was not what scientists expected. Before Voyager 1 crossed, models predicted the galactic field would be oriented differently from the sun's field. The sun's field runs generally radially outward. Though twisted and tangled by rotation and turbulence, the galactic field should be oriented. Based on the large-scale structure of the Milky Way, our region is in the Orion Arm, a minor spiral arm. The galactic field should run generally parallel to spiral arms, so crossing the heliopause should show a rotation of the magnetic field. Not necessarily a dramatic flip, but some significant change marking the transition from sun-dominated to galaxy-dominated field. Voyager 1 detects no such change. The field direction after crossing is essentially the same as before. This causes months of confusion and debate. Eventually, scientists conclude the local galactic field happens to run roughly parallel to the sun's field in this region. Pure coincidence. The field lines in interstellar space just happen to point roughly the same way as the heliosphere's field at Voyager 1's crossing location. Voyager 2's crossing shows a small field rotation about 20 degrees. Not dramatic, but measurable. This reveals the field direction in nearby interstellar space isn't uniform. It varies. At Voyager 1's location, it points one way. At Voyager 2's location, 121 AU away in a different direction. It points slightly differently. This makes sense. The interstellar field isn't uniform like a bar magnet. It's structured, twisted, tangled by plasma currents and stellar influences. But it means we can't easily extrapolate from 2 data points. We have measurements at 2 locations separated by over 100 AU. They're slightly different. How does the field vary between those points? How does it vary? In other directions, we don't know. The magnetic field matters because it affects cosmic rays. Charged particles spiral along field lines as they travel. Field lines act like channels guiding particles. If galactic field lines are oriented favorably, they guide cosmic rays into the heliosphere. If they point wrong, cosmic rays are deflected away. Understanding the local galactic field structure is crucial for understanding cosmic ray exposure on Earth. Cosmic rays affect atmospheric chemistry. They produce isotopes like carbon-14 used for dating. They might influence cloud formation. They contribute to radiation dose for astronauts. Over geological timescales, cosmic ray flux has varied. We see this in isotope records. In ice cores and sediments, some variation comes from Earth's magnetic field changes, some from nearby supernova explosions. Some might come from heliosphere shielding changes as the sun moves through regions of different interstellar pressure. The Voyagers give us a snapshot of current configuration, but that configuration isn't static. It changes as the sun moves through the galaxy. This is shocking discovery number 6. The magnetic field orientation was unexpected, and it varies from one location to another just over 100 AU apart. Galactic cosmic rays are high-energy particles, mostly protons, from outside the solar system, accelerated by supernova shock waves, pulsar winds, and other violent events. They carry energies from millions to trillions of electron volts. Some reach energies beyond what the Large Hadron Collider achieves. The Voyagers measure cosmic ray intensity and composition. Goal is understanding how the heliosphere shields us from galactic cosmic rays. As Voyager 1 moves through the heliosheath, cosmic ray intensity gradually increases, expected. The deeper into the heliosheath, the weaker the shielding, the more cosmic rays penetrate. But the direction cosmic rays come from is surprising. Scientists expected roughly equal intensity from all directions. Instead, there's asymmetry, more from some directions than others. After Voyager 1 crosses the heliopause, cosmic ray intensity jumps to a new level, about 10 to 20% higher than in the heliosheath. This confirms the heliosphere provides shielding. Even the outer heliosheath, billions of miles from the Sun, reduces cosmic ray intensity by 10 to 20% compared to interstellar space. But again, the directional distribution is unexpected. Cosmic rays aren't coming uniformly, clear enhancement from certain directions, deficit from others. Voyager 2 confirms this after crossing. Higher cosmic ray intensity in interstellar space than heliosheath, directional anisotropy. The anisotropy suggests the local interstellar medium has structure. Perhaps nearby sources like old supernova remnants or the galactic magnetic field guides cosmic rays preferentially from certain directions. Interestingly, both Voyagers detect lower cosmic ray intensity from the galactic center direction. Counterintuitive, the galactic center has the highest star density and most supernova explosions. You'd expect more cosmic rays from that direction. The explanation might be that the galactic field is stronger toward the center. Cosmic rays trying to propagate outward from the inner galaxy get trapped and scattered by the field. Fewer reach our local region from that direction. This is still active research. The Voyagers provided first direct measurements of cosmic ray intensity and directionality in interstellar space, but two measurements from two locations don't fully map three-dimensional structure. Future missions will need to explore other directions. This is shocking discovery. Number 7. Cosmic rays come preferentially from unexpected directions. The source distribution doesn't match simple models. So, how did we get here? How did two spacecraft designed for a 5-year mission end up making these discoveries 11 billion miles from home? The journey begins with Jupiter. Voyager 1 reaches Jupiter in March 1979. Voyager 2 arrives in July 1979. The encounters revolutionize understanding of the solar system's largest planet. Jupiter's atmosphere shows far more complexity than expected. The Great Red Spot reveals intricate structure. Before Voyager, astronomers knew the Great Red Spot existed, but they didn't know what caused it or how deep it went. Voyager images show it's a high-pressure system, an anticyclone rotating counterclockwise. The storm rises about 5 miles above surrounding clouds. The color comes from complex organic molecules produced when sunlight breaks down simpler compounds in the atmosphere. The atmosphere has dozens of smaller storms, white ovals and brown barges, each larger than most hurricanes on Earth. These storms interact with each other, sometimes merging, sometimes passing by in complex dances governed by Jupiter's powerful winds and rotation. Lightning flashes in the atmosphere. The lightning is similar to Earth's lightning, electrical discharge between clouds or between clouds and deeper atmospheric layers. But Jupiter's lightning bolts are enormous. some releasing 1,000 times more energy than typical lightning on Earth. Aurora blaze at both poles, similar to Earth's northern and southern lights, but vastly more powerful. Earth's aurora are caused by charged particles from the solar wind colliding with atmospheric molecules. Jupiter's aurora are powered by its rotation and magnetic field. As Jupiter's magnetic field sweeps through space, it picks up charged particles from Io's V-synism. These particles spiral along field lines toward the poles, slamming into Jupiter's upper atmosphere at tremendous speeds. The result is aurora 1,000 times brighter than Earth stretched for thousands of miles across polar regions. Cloud bands show winds exceeding 400 miles per hour. Earth's jet streams reach maybe 200 miles per hour at most. Jupiter's winds are driven by the planet's rapid rotation. Jupiter completes one rotation in just under 10 hours, despite being 11 times wider than Earth. It spins in less than half the time. This creates powerful Coriolis forces that organize the atmosphere into alternating bands of east-flowing and west-flowing winds. But the biggest surprises come from Jupiter's moons. Astronomers had known about Jupiter's 4 large moons since Galileo discovered them in 1610. Iseo, Europa, Ganymede, and Callisto, collectively called the Galilean moons, from Earth. They appeared as tiny points of light. No telescope could resolve surface features. Astronomers could measure their sizes, orbits, and brightnesses, but little else. Voyager would change that. Io, the innermost large moon, was expected to be cold and dead like Earth's moon. Linda Morabito, a navigation engineer, was examining images to determine Voyager 1's precise position. She noticed a strange umbrella-shaped plume extending from Io's limb, a volcanic eruption, the first active volcano ever discovered beyond Earth. Io turns out to be the most volcanically active body in the entire solar system. Voyager discovers 9 active volcanoes during the flybys. Later observations catalogue over 400 volcanic centres. The surface is constantly resurfaced by sulfur and silicate lava, giving Io its distinctive yellow, orange, and red colours. Some volcanic plumes reach heights of nearly 200 m above the surface, material ejected at speeds exceeding 1000 MPa. The volcanic activity comes from tidal heating. Jupiter's enormous gravity, combined with tugs from Europa and Ganymede, constantly flexes Io's interior. This flexing generates friction, generates heat, melts rock, erupts as volcanoes, a process theorized but never confirmed until Voyager. The discovery changed how scientists think about energy sources for geology, not just radioactive decay in planetary interiors. Tidal heating from gravitational interactions can power volcanism and tectonics. This applies to Io, Europa, Enceladus, and potentially exomoons orbiting giant exoplanets. Europa presents a different mystery. Its surface is smooth ice crisscrossed with cracks and ridges. Very few craters suggesting a young surface constantly renewed. The ice appears to be fractured and refrozen in complex patterns. Long linear cracks called line stretch for hundreds of miles. Some regions show chaotic terrain where the ice appears to have broken apart and reformed. The implication is profound. Beneath that ice might be liquid water, an ocean kept liquid by tidal heating, though less than Io's. The same gravitational interactions that tear Io apart might be gently warming Europa's interior enough to keep water liquid beneath the ice shell. Voyager can't prove the ocean exists. Evidence is circumstantial based on surface features and models, but the possibility that Europa might harbour a subsurface ocean makes it one of the most intriguing targets for searching for life beyond Earth. Later missions, particularly Galileo in the 1990s and 2000s, would provide stronger evidence for the ocean. Magnetic field measurements suggesting a conducting layer beneath the surface composition showing salts that might come from an ocean below. But Voyager provided the first hints, the first suggestion that an icy moon might hide an ocean. Ganymede, the largest moon in the solar system, shows a complex surface, old dark terrain covered with music craters, younger, brighter terrain with grooves and ridges. The moon appears to have undergone geological resurfacing at some point in its history. Callisto, the outermost Galilean moon, is heavily cratered. Its surface is ancient, perhaps unchanged for billions of years, a stark contrast to Io's constantly renewing surface. Voyager also discovers Jupiter has rings, faint, made of dust-sized particles, nothing like Saturn's spectacular ice rings. Astronomers had suspected rings might exist, but had never detected them from Earth. Voyager 1 confirms their existence in 1979. The rings are thin and faint, but they're there. The discovery suggests ring systems might be common around giant planets. Perhaps all giant planets have rings, some spectacular like Saturn's, others faint like Jupiter's. By the time Voyagers leave Jupiter, they've returned more data than all previous observations combined. Thousands of images, measurements of magnetic fields, music radiation environments, atmospheric composition, data on 4 major moons and several smaller ones, discovery of a ring system. The mission is a spectacular success, and Saturn is next. Voyager 1 reaches Saturn in November 1980. Voyager 2 arrives in August 1981. Saturn's rings had been observed since Galileo first saw them in 1610, though he didn't understand what he was seeing. He thought Saturn had ears or handles. It wasn't until the 1650s that Christian Huygens realized Saturn was surrounded by a ring. By the 1980s, astronomers knew Saturn had multiple rings separated by gaps: the A ring, B ring, C ring, the Cassini division. A large gap between the A and B rings. But they had no idea of the true complexity. Voyagers reveal each visible ring is actually thousands of individual ringlets, complex structure on scales that couldn't be resolved from Earth. The rings aren't solid or continuous. They're made of billions of individual particles ranging in size from dust grains to house-sized boulders. Each particle orbits Saturn independently following the laws of orbital mechanics. The rings show waves, braids, kinks, and spokes. Dark radial features that rotate with the rings. The mechanism for the spokes wasn't immediately understood. Later analysis suggested they're caused by electrostatic levitation of dust particles above the ring plane. Shepherd. Moons, tiny satellites orbiting near ring edges whose gravity herds ring particles and maintains sharp boundaries. Prometheus and Pandora. 2 small moons flanking the F ring. Keep that ring confined through their gravitational influence. The F ring shows braided structure unlike anything seen elsewhere. 3 or 4 strands that appear to wind around each other. Later observations show the braids change over time as the shepherd moons perturb the ring particles. The level of complexity is astonishing. Saturn's rings aren't just bands of debris. They're a dynamic system where gravity, orbital mechanics, and particle collisions create structure on every scale, from features spanning thousands of miles down to individual particles a few feet across. Density waves propagate through the rings, similar to sound waves, but caused by gravitational resonances with Saturn's moons, where particles orbit at specific ratios to a moon's orbit. The repeated gravitational tugs create waves. These waves compress and rarefy the ring material, creating spiral patterns. Bending waves also appear. These cause the ring plane to warp vertically in response to gravitational perturbations. The rings are thin, incredibly thin, thousands of miles across, but only about 30 feet thick in most places. Thinner than a sheet of paper if you scaled Saturn down to the size of a beach ball. Titan, Saturn's largest moon, was known to have an atmosphere, the only moon in the solar system with a thick atmosphere comparable to a planet's. This had been known since the 1940s when Gerard Kuiper detected methane absorption in Titan's spectrum. Voyager 1 makes a close flyby, passing within 500 miles. The spacecraft sacrifices visiting other targets to make this close approach. The trajectory that allows a close Titan flyby prevents Voyager 1 from continuing to Uranus and Neptune. That's why Voyager 2 takes over for the ice giants. But the Titan encounter is worth it. The atmosphere turns out even thicker than expected. Surface pressure about 1.5 times Earth's at sea level. That's higher pressure than on any other moon or planet except Venus. Composition primarily nitrogen like Earth's, about 95% nitrogen, but with methane and other organic compounds making up the rest. Methane, ethane, propane, acetylene, complex organic chemistry happening in the atmosphere. The surface is hidden beneath opaque orange haze, layers of photochemical smog created when sunlight breaks down methane. The smog particles are tholins, complex organic molecules, similar to the compounds that might have existed on early Earth. Voyager can't see through to photograph the surface. The cameras see only the top of the haze layer, but atmospheric data is fascinating. Temperature, pressure, composition, measurements at different altitudes. Titan has a methane cycle analogous to Earth's water cycle. Methane evaporates from the surface, forms clouds, rains back down. The surface likely has lakes or seas of liquid methane and ethane, rivers and streams flowing with liquid, hydrocarbons, organic chemistry driven by sunlight breaking down methane and creating complex molecules. The temperature at the surface is about minus 290 degrees F. Cold enough that water ice is rock hard, but warm enough that methane can exist as a liquid. Titan becomes another high-priority target for future exploration. The Cassini mission would later orbit Saturn for 13 years. The Huygens probe would land on Titan in 2005, returning the first images from the surface, revealing a world with methane lakes, river channels, and dunes, made of organic sand, but that was decades in the future. For now, Voyager has revealed Titan is a world of extraordinary complexity, a moon with weather, seasons, and a surface shaped by erosion and deposition, the only place besides Earth where liquids flow on the surface, though on Titan, those liquids are methane and ethane, not water. After Saturn, the two Voyagers diverge. Voyager 1 is sent on a trajectory above the solar system plane heading into interstellar space as quickly as possible. It will visit no more planets. Voyager 2 continues to Uranus and Neptune. The only spacecraft to visit these distant ice giants remains so to this day. Uranus in January 1986. Uranus's odd axis tilted 98 degrees relative to its orbital plane. It essentially rolls along its orbit like a barrel rather than spinning like a top. This means poles alternately point toward and away from the Sun during its 84-year orbit. Each pole experiences 42 years of continuous daylight followed by 42 years of darkness. Voyager 2 reveals Uranus's atmosphere as surprisingly bland, few visible cloud features, pale blue colour from methane absorbing red light, winds reaching 560 miles per hour, 10 previously unknown moons, 2 new rings adding to 9 already known. But the most interesting discoveries come from Miranda. Miranda shows bizarre geology. Regions of ancient heavily cratered terrain right next to regions of grooved terrain with parallel ridges and valleys. Enormous cliffs including Verona Rupes estimated at 6 miles high, over 3 times the height of Vas Marinera's walls. On Mars, the surface looks shattered and reassembled. One theory suggests Miranda was broken apart by massive impact, then reassembled from fragments. Different terrain types jumbled together. Another theory invokes tidal heating, though Miranda's current orbit doesn't provide enough stress. Perhaps its orbit was different in the past. The cause remains uncertain, but Miranda definitely experienced something unusual. Neptune in August 1989, the farthest planet from the Sun, nearly 3 billion miles from Earth. Voyager 2's flyby is the culmination of the Grand Tour. 12 years after launch, the spacecraft has successfully visited all 4 outer giants. Neptune was expected to be similar to Uranus, another bland ice giant with little weather. Instead, Neptune shows the most dynamic atmosphere of any planet visited, the Great Dark Spot, an Earth-sized storm similar to Jupiter's Great Red Spot, the Scooter, a bright cloud circling the planet every 16 hours, winds exceeding 1,300 miles per hour, the fastest winds measured on any planet. In the solar system, Neptune's largest moon, Triton, provides another shock. Triton orbits Neptune in the wrong direction, retrograde orbit, opposite to Neptune's rotation, extremely unusual for a large moon. Implication is that Triton wasn't formed alongside Neptune. It was captured probably from the Kuiper Belt. Triton shows active geology, nitrogen ice geysers erupting from the surface. Geysers on a world where surface temperature is minus 391 degree F. One of the coldest surfaces measured in the solar system, yet geologically active. The mechanism is thought to be seasonal heating, even at Triton's distance. Sunlight can warm dark regions beneath translucent nitrogen ice. Nitrogen sublimes, turning directly from solid to gas, building pressure. Eventually, pressure ruptures the surface. Nitrogen gas vents into space, carrying dark particles that fall back as dark streaks. With Neptune, Voyager 2's planetary mission ends. Both spacecraft far exceeded original parameters. They discovered active volcanism on Io, hints of subsurface oceans on Europa, Jupiter's rings, thousands of ringlets in Saturn's rings, Titan's thick atmosphere, Miranda's bizarre geology, Neptune's dynamic atmosphere and fastest winds, Triton's geysers, tens of thousands of images and measurements that transformed understanding of the outer solar system. And they were still functional, still transmitting data, still capable of science. So NASA made a decision. The Voyager interstellar mission would begin, the spacecraft would continue, outward, seeking the boundary where the sun's influence ends. No spacecraft had ever gone that far. Scientists had models and predictions. All would turn out to be wrong. These planetary successes made scientists confident about their predictions for the edge. The models had worked for the planets. Surely they'd work for the heliopause. But the edge of the solar system isn't like a planet. It's a dynamic boundary between 2 plasmas. And it turned out to be far stranger than anyone imagined. The Voyager. Discoveries have profound implications for any future attempt at interstellar travel. They've given us first direct measurements of the environment any interstellar spacecraft would traverse. And the reality is sobering. Voyager 1 has been travelling for nearly 50 years. It's covered about 159 AU, 14.8 billion miles. Sounds impressive until you realise how far it is to even the nearest star. Proxima Centauri, the closest star to our Sun, is 4.24 light-years away, about 268,000 AU. about 25 trillion miles. At Voyager's speed, it would take about 73,000 years to reach Proxima Centauri. 73,000 years. Longer than all of recorded human history. Longer than humans have practiced agriculture. Longer than the time since the last ice age ended. And Voyager isn't even heading toward Proxima Centauri. It's headed in a completely different direction. The star Voyager 1 will pass closest to is Glee, 445 in about 40,000 years. But closest approach means 1.6 light years, 9.4 trillion miles. Voyager won't enter that star's system. It will drift past in the vast emptiness between stars. Voyager 2 will pass within 1.7 light years of Ross 248 in about 40,000 years. Again, it's not close enough to matter. These timescales reveal the fundamental challenge. Distances are so vast that even travelling at tens of thousands of miles per hour is hopelessly slow. To make interstellar travel feasible, you need dramatically higher velocities, at least a few percent of light speed, maybe 10% for reasonable travel times to nearby stars. 10% of light speed is about 67 million miles per hour, about 1/700 times faster than Voyager. At that speed, Proxima Centauri would be about 42 years away. Still a lifetime, but within span of a human career, you could send a spacecraft and possibly still be alive when data starts coming back. But reaching 10% of light speed requires enormous energy, and Voyager discoveries reveal additional challenges. The interstellar medium, though extremely tenuous, isn't empty. About 0.08 atoms per centimetre, mostly hydrogen and helium. At Voyager's speed, this doesn't matter. The spacecraft occasionally hits a hydrogen atom. Impact has negligible effect, but at 10% of light speed, every collision becomes significant. Kinetic energy of impact is proportional to velocity squared. A 10% of light-speeded collision has about 28 million times more energy than a Voyager speed collision. A hydrogen atom hitting a spacecraft at 10% of light speed delivers about 6 electron volts of energy. Doesn't sound like much, but there are a lot of atoms. A spacecraft with 1 square meter. Cross-section travelling at 10% of light speed would hit about 10 to the 14th hydrogen atoms per second. 100 trillion atoms per second. Each collision delivers tiny energy, but they add up. Total power deposited by atomic impacts would be several thousand watts continuously for years. This energy appears as heat in the spacecraft's hull, also as radiation damage. Each high-speed impact can knock atoms out of hull material, creating defects. Over years, this accumulates. Materials become brittle. Electronics can be damaged, and that's just from neutral hydrogen. The interstellar medium also contains charged particles, cosmic rays. Voyager measured cosmic ray intensity in interstellar space at about twice the level in the inner solar system. Cosmic rays are high-energy particles with energies from millions to billions of electron volts, much more damaging than thermal hydrogen. A single high-energy cosmic ray penetrates deep into materials, creating cascades of secondary particles. Over decades of travel, cosmic ray exposure would be significant. Humans aboard would need heavy shielding, electronics would need radiation hardening, biological samples would need protection. Voyager's measurements give us baseline radiation environment. Future missions can use this data to design appropriate shielding. The magnetic field measurements also matter. Charged particle trajectories are affected by magnetic fields. The galactic field is weak only 50 nanotesla, but over vast distances, even weak fields deflect particles. for a spacecraft using a magnetic sail, a proposed propulsion method that music uses magnetic fields to interact with the interstellar medium. Knowing field strength and direction is crucial. Voyager's measurements provide first direct data. The tsunami wave detections reveal interstellar space isn't quiescent. Shock waves from solar storms propagate billions of miles. Other stars probably produce similar disturbances. An interstellar spacecraft might encounter shock waves from distant stellar outbursts. These could temporarily increase density or temperature along the spacecraft's path, might enhance cosmic ray intensity temporarily. Understanding that the interstellar medium is dynamic, not static, is important for planning long-duration missions. The discoveries about heliosphere shape and size also matter. Any spacecraft leaving the solar system must cross the heliopause. Depending on direction, that crossing might happen at 120 AU or 150 AU or beyond. Knowing how far you need to travel to reach interstellar space is important for mission design. The heliopause also represents the last region of significant solar influence. Beyond it, a spacecraft is truly on its own. Communication delays become even more severe. At 120 AU, signals take nearly 17 hours one way. At 100 AU, over 5 days at a light year over a year each way. The Oort cloud presents another challenge. The Oort cloud is a hypothetical shell of icy objects surrounding the solar system, thought to extend from about 2000 AU to as far as 100,000 AU, halfway to the nearest star. Voyager 1 won't reach the inner edge for about 300 years, won't exit the outer edge for about 30,000 years. An interstellar mission, even travelling much faster, would spend most of its journey within the Oort cloud, technically still within the Sun's gravitational sphere of influence. We don't know. Conditions in the Oort cloud. Is object density high enough to pose collision risk? Are there dust grains that could damage a high-speed spacecraft? Voyager won't answer these questions. Its instruments will be dead long before it reaches the Oort cloud. But the fact that Voyager has travelled 50 years and still hasn't reached it gives perspective. The solar system is bigger than we thought. The journey to truly interstellar space is longer than we imagined. All these realities make interstellar travel look extremely challenging, not impossible, but requiring technologies and capabilities far beyond what we currently possess. Advanced propulsion reaching significant, fractions of light speed, robust materials withstanding decades of impacts and radiation, power sources functioning for decades without maintenance, communication systems sending signals across light years, autonomous navigation because round-trip communication times make real-time control impossible. The Voyagers have shown us what we're up against. They've measured the environment we'd have to cross. They've revealed even our local cosmic neighborhood is more complex than we thought. This doesn't mean we shouldn't attempt interstellar travel. It means we need to be realistic about challenges and timescales. Perhaps the Voyager's greatest contribution to future interstellar exploration is showing it's possible to send something beyond the solar system and have it keep working. The engineering that went into these spacecraft, the redundancy, the simplicity, the robustness has enabled them to function far longer than anyone expected. Future interstellar missions will need similar robustness, but magnified. If Voyager can last 50 years, an interstellar mission might need to last 100 years or more. If Voyager can communicate from 15 billion miles, an interstellar mission needs to communicate from 1 trillion miles or more. The challenges are immense, but the Voyagers proved we can build things that work in the interstellar environment, at least for decades. They're a proof of concept that leaving the solar system is possible. On February 14th, 1990, Voyager 1 turned its camera backward for one last look at the solar system. The spacecraft was about 3.7 billion miles from Earth, about 40 AU beyond Neptune's orbit, heading outward toward the helop, still decades away. At that point, NASA commanded Voyager 1 to rotate its scan platform and take a series of images. A family portrait of the solar system, images of 6 planets: Earth, Venus, Jupiter, Saturn, Uranus, and Neptune. Mercury was too close to the Sun, lost in glare. Mars was too small and dim. Pluto was too faint music to detect. In one of those images, Earth appears as a tiny dot, a pale blue dot less than a pixel in size, suspended in a beam of scattered sunlight. Carl Shawn, who'd been a driving force behind including cameras on Voyager and who worked on the Golden Record, saw that image. He was moved to write one of the most profound reflections on humanity's place in the cosmos. He pointed out that everyone who had ever lived on that dot. Every human drama, every war, every romance, every triumph and tragedy, all of it played out on a mote of dust floating in. A sunbeam. From Voyager's vantage point, Earth had no special significance, just one planet among several, smaller than Jupiter, fainter than Venus, indistinguishable except that we know it's there because we came from it. The pale blue dot image connects to Voyager's discoveries at the edge in a profound way. The spacecraft that took that image went on to cross the heliopause. It entered interstellar space. It measured the galaxy beyond the sun's influence. And from out there, from true interstellar space, Earth is even less significant. The entire solar system is a tiny bubble in the vastness of the galaxy. The Sun is one star among hundreds of billions. The heliosphere is one small region in the incomprehensible expanse of interstellar space. The discoveries the Voyagers made revealed that even our local cosmic neighborhood is more complex than we realized. If we are still learning about the boundary between solar system and interstellar space, how much more is there to learn about the galaxy, about the universe? The pale blue dot image is a reminder of scale, of how small we are, of how recent our presence is on cosmic timescales. Earth is 4.5 billion years old. Humans have existed for maybe 300,000 years. Civilization for maybe 10,000 years. Space exploration for less than 70 years. The Voyagers launched 49 years ago. They've been travelling for a human lifetime and they've barely left the solar system. They're in the very beginning of interstellar space just beyond the heliopause. The nearest star, Proxima Centauri, is 4.24 light-years away. At Voyager's speed, about 73,000 years to get there. The spacecraft aren't headed toward Proxima Centauri. They'll pass nearest to other stars in about 40,000 years at distances over a light-year. True interstellar travel, travelling between stars, visiting other planetary systems, remains far beyond our capability. The Voyagers are interstellar in the sense they've left the heliosphere. They're in the space between stars. But they're not travelling to other stars. They're just drifting. And yet, what they've accomplished is extraordinary. 2 spacecraft built with 1970s technology have travelled farther than anything humans have ever made. They've visited worlds no one had ever seen up close. They've crossed a boundary no spacecraft had ever reached. They've measured conditions that had only been theoretical. They've shown us the universe is always more complex than our models suggest. That there are always surprises waiting. That exploration reveals things we didn't know we didn't know. The pale blue dot image captures that spirit of exploration, looking back at where we came from, seeing it with new eyes, recognizing both how precious it is and how small it is, and then turning around and continuing the journey outward into the unknown. By 2026, nearly 50 years after launch, both Voyagers are still operational. This is extraordinary. The spacecraft were designed for 5-year missions. They've lasted 10 times longer than their design lifetime. But they're dying. Slowly, inexorably. The plutonium in their RTGs decays, power output drops, and there's no way to replace or recharge the power sources. Voyager 1 is currently about 159 AU from the Sun, about 14.8 billion miles. Signal takes over 22 hours to reach Earth. Voyager 2 is about 132 AU, about 12.3 billion miles. Signal takes about 18 hours. Both spacecraft are moving at roughly 38,000 MP relative to the Sun. Voyager 1 is travelling faster and is farther away every year. Voyager 1 moves about 3.6 AU farther from the Sun. Voyager 2 moves about 3.3 AU farther per year. The power situation is critical. In 2026, Voyager 1 has about 249 watts remaining. Instruments and systems need about 245 watts to operate. The margin is only 4 watts. Every few months, engineers shut down another heater or power a system down to standby mode. The spacecraft are getting colder. Some instruments have already frozen and stopped working. In 2020, NASA shut down the heater for Voyager 2's cosmic ray. Instrument! The instrument dropped to minus 74 degrees F. Engineers expected it to fail. Instead, it kept working. 1970s engineering running 40 degrees below design temperature. Still returning data, but time is running out. By around 2025 to 2027, there won't be enough power to run core systems and any science instruments. Engineers will have to start shutting down instruments permanently. By 2030, maybe 2032 at latest, the power budget will be exhausted. The spacecraft won't have enough power to communicate. With Earth, transmitters will fall silent. The Voyagers will continue to travel. They'll still be intact. Solar panels and antenna and RTGs still attached, but dead. No power to run anything, no way to communicate. Drifting silently through the void, and they'll keep drifting for an incomprehensibly long time. Voyager 1 is heading generally toward the constellation of Fucus in about 40,000 years. It will pass within 1.6 light-years of the star, Gliese 445, closest approach to any star in Voyager. One's foreseeable future, 1.6 light-years is about 9.4 trillion miles. Voyager won't enter that star's planetary system if it has one. It will just drift past in the vast emptiness between stars. Voyager 2 is heading toward the constellation Parvo and Indis. In about 40,000 years, it will pass within 1.7 light-years of the star Ross 248. After those close approaches, the Voyagers will continue wandering the galaxy. They might eventually pass close to other stars. Over millions of years, encounters with stars and their gravitational fields will gradually change the Voyagers' trajectories. Over billions of years, the spacecraft will orbit the galactic center along with all the other stars, completing one orbit every 225 million years or so. The golden records will still be attached. Gold doesn't corrode in space. No oxygen, no water, nothing to degrade the metal. The records should remain intact for hundreds of millions, possibly billions of years. The chance of any civilization finding them is essentially zero. Space is too vast, the Voyagers are too small, and they're not aimed at any particular star. but they'll be out there. Humanity's first ambassadors to interstellar space, carrying a message from a species that might no longer exist by the time the spacecraft complete even one orbit of the galaxy. Each Voyager carries a golden record, a 12-in gold-plated copper disc containing sounds and images from Earth. The record is designed to last for billions of years in the vacuum of space. Gold doesn't corrode or oxidize. There's no oxygen in space, no water, nothing to degrade the metal. Information is physically etched into the surface, not stored magnetically or electronically. The grooves contain analog audio information similar to a vinyl record, but instead of music throughout, the record contains a carefully curated selection of Earth's sounds, images, and music. Even if the spacecraft's electronics fail, even if power dies completely, the record will remain intact and readable, assuming you have the right equipment. The sounds on the record were carefully chosen to represent Earth's diversity. Natural sounds, wind rustling through trees, rain falling, thunder rumbling, surf breaking on a beach, volcanic eruptions with their deep rumbling and explosive cracks, earthquakes with ground shaking low-frequency sounds, songs of humpback whales recorded in the oceans, these haunting complex vocalizations that can travel for hundreds of miles underwater, birdsong from multiple species, the cheerful chirping of crickets, frogs croaking in a pond, dogs barking, sounds meant to convey the biodiversity of Earth, human sounds, a baby crying, that universal sound of new life, human footsteps walking, laughter, both male and female, a heartbeat, the rhythm that sustains human life, the sound of a kiss between a mother and child, tools being used demonstrating human technology, a hammer striking an anvil, metal on metal, a saw cutting wood, the rasp of teeth through timber, a tractor engine running, transportation sound showing human mobility, a horse and cart, an ancient form of transport, a train whistle, the sound of the industrial age, a jet aircraft roaring overhead, a Saturn V rocket launch, the thunderous power that sent these very spacecraft to the stars, music from around the world and across human history. The selection was perhaps the most difficult part. How do you choose music to represent all of humanity? Buck's Brandenburg Concerto. Number 2. Mathematical precision and emotional depth. Beethoven's Fifth Symphony, one of the most recognized pieces in Western classical music. Beethoven's String Quartet Number 13. More intimate and contemplative. Mozart's The Magic Flute, combining drama and beauty. Stravinsky's The Rite of Spring, revolutionary and primal. But the committee knew Western classical music couldn't represent everyone. Traditional music from Java, the gamelan orchestras with their intricate rhythms. Music from Sagel with complex poly-W rhythms and call and response patterns. Pygmy music from Zaire, now the Democratic Republic of Congo. Aboriginal songs from Australia. Some of the oldest continuous musical traditions on Earth. Panpipe music from Peru, echoing across the Andes, shakuhachi music from Japan, meditative and spare, Chinese traditional music with its distinctive pentatonic scales, Indian classical music with its complex ragas and talas, blues from the American South expressing pain and resilience, jazz, Louis Armstrong's distinctive trumpet and vocals, rock and roll, Chuck Berry's guitar and lyrics about American teenage life, Georgian choir music with its dense polyphonic harmonies, each piece chosen to represent not just a genre or culture, but something essential about human expression. The selection committee led by Carl Shawn struggled with difficult choices. Every piece of music, Every sound represented thousands of alternatives that couldn't be included. There were arguments, debates, compromises. Some committee members wanted more contemporary pop music. Others felt classical music better represented humanity's artistic achievements. Some wanted religious music, hymns, and sacred chants. But which religion, Christianity, Islam, Hinduism, Buddhism, indigenous traditions, including one might seem to slight others? The committee tried to balance representation with quality, tried to include music from many cultures, though inevitably some were overrepresented and others underrepresented. How do you represent all of human culture on one disc? What defines us? What should we preserve? What would we want an alien civilization to know about us? Greetings in 55 languages from ancient Akkadian to modern English. Adian, a language dead for thousands of years but representing humanity's ancient roots. Sumerian, another ancient language from Mesopotamia. Hittite, Latin, ancient Greek, modern languages spoken by billions. Mandarin Chinese spoken by over 1 billion people, Spanish, Hindi, Arabic, English, French, Russian. Each greeting is brief, just a few sentences, peace and friendship. Greetings from the children of planet Earth. We hope someday, having solved the problems we face, to join a community of galactic civilizations. This record represents our hope and our determination and our goodwill in a vast and awesome universe. Similar sentiments in dozens of tongues. The greetings emphasize peace, friendship, and goodwill. A hopeful message from a species still struggling with war and division. Then there are the images, 116 pictures encoded digitally on the record. The images aren't stored as visible pictures. They're encoded as audio waveforms that can be decoded into visual images. Each image is translated into a series of tones representing brightness values for each pixel. Mathematical and physical definitions to explain our scientific understanding. Diagrams showing basic mathematics. Numbers in binary. Definitions of physical units. Time, distance, mass. Chemical structures showing atoms and molecules. DNA, structure, the double helix that carries genetic information in Earth life. Atomic structure showing electrons orbiting nuclei. The solar system structure showing the sun and planets. Earth's position as the third planet. Earth seen from space. The blue marble floating in blackness. Landscape showing Earth's diversity. Mountains rising to the sky, deserts with wind-sculpted dunes, forests with dense vegetation, oceans with waves and beaches, human anatomy showing the structure of our bodies, reproduction, showing how humans create the next generation. These images were controversial. Some committee members thought they were too explicit, but others argued that any intelligent species would need to understand human biology. People of various cultures, ages, and activities, a family eating a meal together, children playing, athletes running and jumping, people working, demonstrating human labor, architecture from different civilizations, the Great Wall of China, the Taj Mahal, modern skyscrapers, traditional houses from various cultures, food showing what and how humans eat, art, paintings, and sculptures demonstrating human creativity, IT technology showing tools, machines, telescopes, a supermarket showing the modern system of obtaining goods, a traffic jam showing urban transportation challenges and perhaps human overconsumption, a page from Newton's Principia showing the mathematical laws that govern motion. The images were encoded as audio signals, a technology that would have been familiar to anyone in 1977 who'd seen early television or slow-scan television. Lines scan across the image and brightness at each point is encoded as an audio frequency. If the record is ever found by an extraterrestrial civilization, they would need to figure out that certain audio sections, music, encode images. Not an impossible task for a civilization capable of retrieving a spacecraft in interstellar space. Clues are provided in instructions etched on the record's aluminum cover. The aluminum cover is itself a marvel of information. Encoding. It shows pictograms explaining how to play the record. The rotation speed 16 2/3 revolutions per minute, an oddly specific number chosen for technical reasons. The position and configuration of the stylus to track the grooves. Diagrams showing how to decode images from audio signals. Binary representations of the timing and scanning parameters needed to reconstruct the images. A pulsar map showing Earth's location relative to 14 pulsars. Pulsars are rotating neutron stars that emit regular pulses of radio waves. Each pulsar has a unique period like a cosmic fingerprint. By showing the periods and directions to 14 pulsars, the map provides a way to locate Earth in both space and time. The same map was included on the Pioneer Plus launched a few years earlier. The map uses pulsar periods as cosmic timestamps and distance markers, since pulsar periods slowly change over time as the pulsars lose energy. The specific periods shown indicate when the record was made. Creating the golden record was an enormous collaborative effort. Scientists, artists, musicians, linguists, anthropologists all contributed. John Lomberg created many of the diagrams and images. Andrew selected many of the sounds and helped choose the music. Frank Drake designed the pulsar map. Linda Salmon Shawn drew the figures of humans on the cover. They had only months to complete the project. The Voyager spacecraft were being built on NASA's tight schedule. Launch windows were inflexible because of the rare planetary alignment. The record had to be finished, manufactured, and installed before launch. Technical constraints added to the challenge. The amount of data that could fit on one disk was limited by the groove spacing and the record's diameter. Audio quality had to be balanced against duration. Higher quality audio uses more space, limiting what could be included. Image resolution had to be balanced against the number of images. More images meant lower resolution for each. Every decision involved trade-offs. Every inclusion meant something else had to be left out. The golden record was more than a scientific project. It was a philosophical statement, an attempt to answer profound questions. What does it mean to be human? What should we tell another intelligence about ourselves? What's worth preserving for eternity? What transcends our differences and speaks to our common humanity? There were debates and compromises. What music to include? Western classical music was familiar to the committee, but was it representative of humanity should pop music be included? Rock and roll was controversial in some cultures. Religious music, which religions? The committee tried to balance representation with quality. They chose pieces they felt were aesthetically significant and culturally important. They tried to include music from many cultures, though inevitably some were overrepresented and others underrepresented. The images were similarly debated. Some committee members wanted to include images of war, poverty, disease to show the full range of human experience. Others argued we should present our best face to the cosmos, showing achievements and aspirations. The final selection emphasized positive aspects, while including some hints of our challenges. There were also technical constraints. The amount of data that could fit on one disk was limited. Audio quality had to be balanced against duration. Image resolution had to be balanced against the number of images. Every decision involved trade-offs. The golden record was more than a scientific project. It was a philosophical statement, an attempt to answer the question, what does it mean to be human? What should we tell another intelligence about ourselves? Carl Sagan and his team knew the chance of the record ever being found was vanishingly small. The Voyagers are tiny objects in the vastness of space. The galaxy contains hundreds of billions of stars. Space between stars is incomprehensibly vast. The probability that either Voyager will pass close enough to another star system to be detected is essentially zero. And, even if one did pass close to a star system, the probability that a technologically advanced civilization exists there at the right time is even smaller. Most stars don't have planets. Most planets don't have conditions suitable for life. Most life doesn't evolve intelligence. Most intelligent species might not develop technology capable of interstellar observation and retrieval. The golden record is more likely to be destroyed than discovered. In billions of years, the Voyagers might collide with something, a planet, an asteroid. Even a tiny dust grain at the wrong angle could catastrophically damage them. They might fall into a star. They might be destroyed by radiation over unimaginable time spans. But the act of creating the record was meaningful for us. It forced us to think about how we would explain ourselves to someone who knows nothing about us. What's important? What's universal? What transcends culture and time? The Golden Record is a snapshot of Earth in 1977. Some of the languages included are now extinct or endangered. Some of the music is no longer performed. Some of the images show things that no longer exist. But it's a time capsule, a message in a bottle thrown into the cosmic ocean. A declaration that we were here, that we existed, that we had thoughts and feelings and culture and dreams. If it's never found, that's okay. The value was in the creation, not the discovery. The value was in thinking about what matters, what endures, what we want to say about ourselves. And now that record is in interstellar space attached to Voyager 1 travelling at 38,000 mph through the interstellar medium that the spacecraft helped us discover. Carried on a vehicle built by a species that has existed for maybe 300,000 years. A mere eye-link on cosmic timescales in 40,000 years. When Voyager 1 passes within 1.6 light-years of Giza, 445 will anything of human civilization remain? Will Earth still be habitable? Will we have spread to other stars? Will we have gone extinct? No one knows. But the Golden Record will still be there, still intact, still carrying its message. A testament to a moment when a young species looked up at the stars and dared to send a part of itself outward into the unknown. The Voyager program cost about $865 million total from start through Neptune encounter in 2026. That's several billion, but spread over the decades of the mission, it's a remarkably small investment for the return. 4 planets explored in detail. Dozens of moons discovered or studied, first observations of volcanism beyond. Earth, first hints of subsurface oceans on icy moons, first measurements of the termination shock, first crossing of the heliopause, first direct sampling of the interstellar medium. Every textbook about the outer solar system uses images from Voyager. Every model of the heliosphere incorporates Voyager data. Every discussion of interstellar space references what the Voyagers found. The spacecraft rewrote our understanding of the solar system and its boundary. They showed that Io is geologically active, driven by tidal heating. This discovery changed how we think about energy sources for geology. Not just radioactive decay in planetary interiors, Tidal heating from gravitational interactions can power volcanism and tectonics. This applies to Io Europa, Enceladus, and potentially exomoons orbiting giant exoplanets. They suggested Europa might have a subsurface ocean. This has driven decades of mission planning. Future missions to Europa are designed to search for signs of life in that ocean. If life exists there, it would prove life can arise independently in multiple locations, even in environments very different from Earth. They reveal the complexity of Saturn's rings, thousands of ringlets, shepherd moons, resonances, music waves. The rings are a natural laboratory for studying orbital mechanics and disk dynamics. Principles learned from Saturn's rings applied to protoplanetary disks around young stars, to accretion disks around black holes, to galaxy disks. They explored Uranus and Neptune, the only spacecraft ever to visit those planets. Everything we know about their atmospheres, magnetic fields, and moons comes primarily from Voyager 2's brief flybys, and then after the planets, they continued into the heliosheath, across the termination shock, through the magnetic highway, across the helop into interstellar space. They measured the distance to the helop and found it farther than predicted. They measured the shape of the heliosphere and found it asymmetric. They measured the properties of the interstellar medium and found them different from models. They detected tsunami waves from solar storms propagating through interstellar space. They measured the galactic magnetic field and found it oriented unexpectedly. They mapped cosmic ray intensities and found anotropies no one predicted. Every one of these findings required scientists to update their understanding, to revise models, to reconsider assumptions. This is the value of exploration, not just to confirm what we think we know, but to discover what we don't know, to find the surprises, to learn that reality is more interesting than our theories. The Voyagers were designed to explore the outer planets. They succeeded at that. But their greatest legacy might be what they discovered afterward. The evidence that we still don't fully understand, even our own cosmic backyard. NASA is planning a follow-up mission called the Interstellar Probe. It's still in the concept stage with no firm launch date or budget. But the science goals are clear. Answer the questions the Voyagers raised. The Interstellar Probe would be designed, from the start for an interstellar mission, more power, longer lifespan, better instruments, faster velocity. The goal is to reach 500 to 1000 AU within 50 years, 5 to 10 times farther than the Voyagers have travelled. To achieve this, the spacecraft would need to travel at roughly 80,000 to 160,000 mph, about twice Voyager's speed or more. This requires either a more powerful launch system or a close solar flyby using solar thermal propulsion or some other advanced propulsion technology. The science goals include exploring the heliosphere's nose and tail in more detail. Voyager 1 crossed near the nose, Voyager 2 crossed toward the side. But what about the tail? How far does it extend? What's its structure? The Interstellar Probe would also explore the outer heliosphere more systematically. Voyager took point measurements along two trajectories. The Interstellar Probe could map larger regions, measuring how properties vary over distance and direction, and it would travel much farther into the interstellar medium. 500 to 1000 AU is still incredibly close to the Sun on galactic scales, but it's far enough to see if the interstellar medium properties Voyager measured are typical, or if they vary significantly over larger distances. The mission could also search for the heliopause bow shock if it exists. Models predict a bow shock in the interstellar medium somewhere around 140 to 230 AU. But given how wrong models were about the heliopause itself, the bow shot could be anywhere. The interstellar probe might find it or might not. Either result would be scientifically valuable. The spacecraft could carry advanced particle detectors to better characterize galactic cosmic rays, magnetometers to map the galactic magnetic field, plasma wave instruments to detect turbulence and waves in the interstellar medium, possibly even a camera to image the solar system from outside, taking a family portrait from interstellar space. But the mission is decades away. Design work is ongoing, funding hasn't been secured, even if everything goes perfectly. Launch wouldn't happen until the 2030s at earliest. And the spacecraft wouldn't reach 500 AU until the 2080s. The scientists designing the mission probably won't live to see its primary results. This is the reality of interstellar exploration. The timescales are longer than human lifetimes. The Voyager's launch when many of the scientists analysing their current data weren't even born. The engineers maintaining the deep space network weren't alive when the spacecraft were built. The people who will see the Voyager's last transmissions are likely in elementary school or younger today. Science on these timescales requires institutional commitment, continuity across generations, a willingness to start projects whose conclusions you won't live to see. But that's what exploration requires. Lewis and Clark explored the western United States, but settlement took generations. Mellin's expedition circumnavigated the globe. But he died before the voyage was complete. Apollo landed humans on the moon, but we haven't returned in over 50 years. Progress isn't linear. It's fits and starts. Periods of rapid advancement followed by consolidation or even retreat. The voyages represent a particular moment in history, a moment when funding was available, technology was adequate, planetary alignment was favourable, and institutional will existed to attempt something unprecedented. That moment might come again. The interstellar probe might launch. Humanity might send more spacecraft into the interstellar medium, or it might not. The Voyagers might remain for decades or centuries the only spacecraft to have directly sampled interstellar space. Either way, what they discovered stands. The data exists, the measurements are recorded, the surprises are documented. Future missions will build on what the Voyagers learned. But even if no follow-up mission ever happens, the Voyagers achieved something permanent. They showed us what's out there at the edge of the solar system in the space between stars. They showed us it's stranger, more complex, more dynamic than we thought, and they showed us we still have so much to learn. Tonight we explored the shocking discoveries Voyager made at the edge of the solar system. 2 spacecraft launched in 1977 with computers less powerful than a modern calculator built to last 5 years. Still operational nearly 50 years later. They visited Jupiter and saw volcanism on Io, the first active volcanoes beyond Earth. They saw Europa's cracked ice surface, hinting at a subsurface ocean. They discovered Jupiter's ring system. They visited Saturn and revealed thousands of ringlets in the rings. They studied Titan's thick atmosphere. They measured magnetic fields and radiation environments. Voyager 2 visited Uranus and Neptune, the only spacecraft to ever reach those distant worlds. It photographed Miranda's fractured terrain. It discovered Neptune's great dark spot and measured winds exceeding 1,300 miles per hour. It studied Triton's geysers erupting on one of the coldest surfaces in the solar system. And then they kept going into the region beyond the planets. Toward the edge, they crossed the termination shock where the solar wind slows down. They travelled through the helio sheath, the turbulent boundary region. They discovered the magnetic highway. an unexpected structure no one predicted. Voyager 1 crossed the heliopause on August 25th, 2012 at 121 AU, far beyond where models predicted. Voyager 2 crossed on November 5th, 2018 at 119 AU. They found that the heliopause isn't where we thought. 2.4 billion miles farther than predictions. They found that the shape is asymmetric, not the symmetric bubble scientists expected. They found that the transition is complex with oscillations and unexpected music structures. They measured the interstellar medium directly for the first time. Density, temperature, pressure, all slightly different from predictions. They detected tsunami waves from solar storms propagating through interstellar space. They measured the galactic magnetic field and found it oriented differently than expected. They mapped cosmic ray intensities and found anotropies that revealed structure in the local interstellar environment. 7 major discoveries. Every prediction was wrong in some way. Not completely wrong. The basic picture was right, but every detail, every specific number, every quantitative forecast was off. This is what exploration does. It tests our understanding against reality. And reality is always more complex than our theories. The Voyagers taught us humility. We thought we understood the edge of the solar system. We built sophisticated computer models. We ran simulations for years. We made confident predictions about where the boundary would be, what shape it would have, how the transition would occur. We wrote textbooks explaining the heliosphere, drew diagrams showing the heliopause as a neat spherical boundary, published papers calculating the exact distance where Voyager would cross. And then 2 spacecraft actually went there and measured it, and we learned we were wrong about almost everything, not fundamentally wrong about the physics. The basic picture was correct. Solar wind does meet interstellar medium. A boundary does form where their pressures balance. Cosmic rays are more intense beyond that boundary. But every specific prediction, every quantitative detail turned out to be incorrect. The distance was wrong by billions of miles. The shape was asymmetric when we predicted symmetric. The transition took years when we expected weeks. The magnetic highway wasn't predicted at all. The interstellar medium properties didn't match our estimates. The magnetic field orientation surprised us. The cosmic ray directionality wasn't what we anticipated. 7 major discoveries, 7 ways that reality surprised our best theories. This is how science actually works, not the neat linear progression often portrayed in textbooks, not a simple path from hypothesis to confirmation, but a messy process of prediction, measurement, surprise, and revision. We build models based on the best available data. We make predictions. We test those predictions. When reality doesn't match, we learn something new. We update our models. We refine our understanding. And then we make new predictions to be tested. The Voyagers are a perfect example of that process. Scientists made honest predictions based on solid physics and the data available. Those predictions turned out to be wrong, music in important ways. Not because the scientists were incompetent or careless, but because the universe is more complex than any model can capture. There were factors scientists hadn't accounted for, properties of the interstellar medium they'd estimated incorrectly, dynamics of the boundary they hadn't anticipated, phenomena like the magnetic highway that no one had predicted could exist. And that's okay. That's how we learn. The wrong predictions weren't failures. They were opportunities to discover something new, to refine our understanding, to build better models for the next generation of spacecraft. The spacecraft are dying now, slowly, inexorably. The plutonium in their RTGs decays, power output drops steadily, about 4 watts per year, every year without exception. Instruments are being shut down one by one to conserve energy. Heaters turned off, letting systems freeze. Backups activated as primary systems fail. Engineers performing triage, deciding what to save and what to sacrifice. By 2030, maybe 2032 at the latest, there won't be enough power left. The transmitters will fall silent. The last signal will fade into the cosmic. Background noise and the deep space network will no longer hear anything from that point in the sky. But they'll keep travelling 38,000 mph forever, not slowing down because there's no friction in space, not stopping because there's nothing to stop them, just drifting outward year after year, decade after decade, century after century, moving through the interstellar space. They helped us discover through the medium they measured for the first time past shock waves from solar storms and stellar outbursts, through varying densities and magnetic field structures, all unobserved, now because their instruments are dead, all unrecorded because they can no longer communicate, but still happening, still real, still there, carrying the golden records with sounds and images from a planet billions of miles behind them. Bach and Beethoven and Chuck Berry drifting through the void. Greetings in 55 languages that no one will hear. Images of Earth and humans and our solar system that no one will see unless, by some infinite decimal, chance they encounter another civilization. In 40,000 years, they'll make their closest approaches to other stars. Voyager 1 passing within 1.6 light-years of GIS 445. Voyager 2 passing within 1.7 light-years of Ross 248. Still over a light-year away from anything. Not close enough to say they've reached another star system. Not close enough for any gravitational interaction. Just passing by in the vast emptiness. The chance of anyone finding them is essentially zero. Space is too vast. The galaxy contains hundreds of billions of stars. The volume of space is incomprehensibly large. The voyages are too small, too cold, too dark to detect except at very close range. And they're not aimed at any particular star. They're just drifting in whatever direction their last trajectory correction sent them. But they'll be out there for millions of years. Billions of years. Potentially until the sun burns out and becomes a white dwarf. Until the galaxy itself changes in ways we can barely imagine. Humanity's first ambassadors to interstellar space. Proof that a species that evolved on one small planet learned to build machines that could leave that planet, leave their homeworld, leave their solar system, and venture into the galaxy beyond, even if we never hear from them again, even if they never encounter another civilization, even if they eventually fall into a star or are destroyed by a collision, they will have served their purpose. They explored the outer planets and revolutionized our understanding. They crossed the boundary and measured interstellar space for the first time. They showed us that our models were wrong and the universe is more complex than we thought. They proved that we can build machines that work in the harshest environment imaginable. Machines that last far longer than their design lifetime. Machines that can venture into the unknown and send back knowledge. And the discoveries they made, the data they returned, the knowledge they gave us, that's permanent. That can never be taken away. Future missions will build on what Voyager learned, the interstellar probe. If it's ever built, we'll use Voyager's discoveries to plan its trajectory and design its instruments. Future textbooks will reference Voyager's findings about the heliosphere and interstellar space. Future scientists will study Voyager data for decades to come, finding new insights, music we haven't noticed yet. The measurements exist in NASA's archives. The images are stored and backed up. The knowledge has been integrated into our scientific understanding. The Voyager showed us the edge of the solar system. They showed us that even at that edge, even at a boundary we thought we understood, reality is stranger and more wonderful than we imagined. They showed us that exploration is about more than confirming what we think we know. It's about discovering what we don't know, finding the surprises, learning that our theories, no matter how sophisticated, are always approximations of a more complex reality. They showed us humility in the face of the universe, showed us that we're still learning about our own cosmic backyard, still discovering basic facts about where the solar system ends and interstellar space begins. If we're still learning about that, imagine how much we don't know about the galaxy, about the universe beyond, about the cosmos as a whole. 2 spacecraft built with 1970s technology, computers with less memory than a microwave oven, transmitters weaker than a light bulb, power systems based on radioactive decay, travelling for nearly 50 years, still teaching us, still surprising us, still showing us that the universe is more interesting than we imagined, until the day they fall silent and drift into the eternal night, carrying their message to the stars, a message from a species that dared to explore, that dared to send a part of itself into the unknown, that dared to ask what lies beyond, and found answers stranger and more wonderful than anyone predicted. Not close enough to say they've reached another star system. The chance of anyone finding them is essentially zero. Space is too vast. The galaxy is too large. The Voyagers are too small. But they'll be out there, humanity's first ambassadors to interstellar space. Proof that a species evolved on one small planet learned to explore beyond its solar system. And the discoveries they made, the data they returned, the knowledge they gave us, that's permanent. Future missions will build on it. Future scientists will reference it. Future textbooks will include it. The Voyagers showed us the edge of the solar system, and they showed us that even at the edge, even at the boundary we thought we understood, reality is stranger and more wonderful than we imagined. That's the spirit of exploration, not just confirming what we think we know, but discovering what we don't know, finding surprises, learning that the universe is always more complex, always more interesting, always more mysterious than our best theories suggest. 2 spacecraft built with 1970s technology, travelling for nearly 50 years, still teaching us, still surprising us until the day they fall silent and drift into the eternal night, carrying their message to the stars.